So what we're going to be taking a look at is some three-dimensional shapes of some of the Lewis structures that we've been talking about so far. We use a method that's referred to as VSEPR, VSEPR, which we're going to talk about kind of in more depth next class. Today we're just kind of scratching the surface of what shapes we have and kind of some information about them. So the first shape we have is in the linear family. We refer to this shape as linear. Notice it's a straight line. So it has a bond angle of 180 degrees. So we're going to be taking a look at bond angles of all of the shapes today. The ones that I'm going to include on this kind of little chart to help us are the ones that you'll be responsible for. So for the linear family, it has a 180 degree bond angle, and the other thing to point out is the polarity of it. So this is a substance that is nonpolar. It's nonpolar. Remember, polarity has to do with the electron distribution. So taking a look at this atom, it's going to be nonpolar because the electrons are going to be shared equally. So if you think back to last class when we were talking about the polarity, symmetry also plays a role, but it's more of the symmetry of the atom. So if we had, for example, let's say we had HC with a N versus C with two oxygens. So carbon dioxide here would be nonpolar because it has this exact same thing bonded on either side. While this top one, which is cyanide with a hydrogen, would be polar because of the difference in electron distribution from the nitrogen, which would have a triple bond versus the hydrogen. So this would be a polar example of a linear substance. This would be nonpolar. So for any of the things that we're discussing today, when we say nonpolar, we're assuming nonpolar when it's symmetrical. If it is asymmetrical, like the example up here, so we have a different atom, such as a hydrogen and a nitrogen in this example, it's going to have a different electron distribution. So the linear family only has one member, linear. As we continue on, we're going to have more and more members of the families as we go on. The next shape we have is trigonal planar. So one thing to point out here is, so the central atom is this pinkish red color, and then the other atoms are symbolized by the white color. So they're white atoms. So these are both members of the trigonal planar family. The first one we have is trigonal planar. When we do the three-dimensional modeling of this, you'll see that all of the molecules are in the same plane. So if you were to cut it in half, you would have two equal parts. Its bond angle is 120 degrees, and it is nonpolar because it has an even distribution of the charge. So these are both members of the trigonal planar family. The next one, it looks a little bit different, and that's because it actually has a lone pair of electrons on the top. So the thing about this, they're members of the same family because the electrons are there. There's no question of the electrons. It's just when you're looking at the molecular shape of a molecule, you can't see the electrons. So when we take a look at it, we only see the two atoms. We have a lone pair of electrons on the top, which this results in the shape that we refer to as bent. So bent is a little bit different than linear because it's not in a straight line, and it has to do with these electrons. So if you take a look, these both look almost identical if you just look at the electron densities around. Some of them you have electron. In this one case, you have electrons. In the other case, you have actual atoms. So the bond angle of the bent shape here is actually a little bit less than 120. I'm going to write less than 120 degrees. It's usually around 118, 117. And the reason why it's less has to do with the electron. The electron lone pair up at the top ends up taking up a little bit more space, forcing the two atoms to be a little bit closer together. So it's usually 118, 117, so it's 2 or 3 degrees. There are a lot of factors here that we're not going to be getting into that affect exactly what the angle is. We're just kind of taking a look at approximates with that. Big picture here, though, I just want you to know the trigonal planar family's bond angle is 120 degrees. I'm not going to ask you to differentiate between trigonal planar and this bent shape. They just overall it has a 120 degree bond angle. The main difference here, other than the obvious shape difference, is that this ends up being polar. Anytime you have a lone pair of electrons on the central atom, it results in a polar atom. There is an exception to this, but for our purposes, most of the time, those electrons result in a polar substance. Moving on to the tetrahedral family, we now have 3 members of the family. So following the pattern, we have the first one, which is a tetrahedral. Remember, tetra from naming means 4, so we have 4 bonding areas in these examples. The bond angle for a tetrahedral is 109.5. And because it has an even electron distribution, this results in a nonpolar substance. So we have tetrahedral. The next one is trigonal pyramid. If you compare this to the trigonal planar, this is the middle atom is actually kind of propped up in the middle. It's sitting on the bottom 3 atoms, while on the top one they're all flat. Again, in the modeling activity you're going to be doing, you're going to see this. But this, again, has a bond angle a little bit less than 109.5, but it is polar, and that's because there's a pair of electrons on the top, which contribute to the little bit difference in bond angle. And then the last example, it looks very similar to the other example we have. This is also bent. This specific bent is a member of the tetrahedral family because there's 2 areas of electrons. So kind of electron clouds there. So your math teacher probably wouldn't like this, but I'm putting 2 less than signs because it's less than this one. So in reality, a trigonal pyramid is about 107. A bent is about 104. So this is smaller than this, and this is smaller than this. Okay, so bent has the smallest bond angle of all of them, and it is also polar. Again, I want you to know tetrahedral 109.5. So just to kind of point out, I'm going to put 4 in quotes here. Tetrahedral, we have 4 bonding areas, whether it's 4 atoms or fewer number of atoms and some electron pairs. Trigonal planar, we have 3 bonding areas in all of them. And linear, we have 2 bonding areas. So that's kind of something to keep in mind. Now, these 3 families are the most important of the bond of the shapes that we're going to talk about and the shapes that you'll be responsible for. The last 2 you do not need to know as in such great detail because they become a little bit more complex as we go through. So continuing on, we have the trigonal bipyramidal. The shape of this one is called bipyramidal because if you take a look, if you kind of connect where your atoms are, you kind of have 2 pyramids. You have a pyramid on the top and a pyramid on the bottom if you connect it with flat sides. But that's why this is referred to as trigonal bipyramidal. So this first one, that's its name, trigonal bipyramidal. Again, this is a nonpolar substance because it has a symmetrical appearance. So this is where the names start getting a little bit more creative. Following the same pattern, we have one area of from a lone pair, which this one we refer to as a seesaw. You can kind of think of this top part as the part of the seesaw that goes up and down, and it kind of tilts back and forth. That's why it's referred to as that. The big thing here is that that's polar. The next one, just as creative, is referred to as T-shaped because it looks like the letter T, which is also polar. This has two areas from the lone pairs because it has two lone pairs. And last but not least, we have another linear. The linear, we did an example that like this. It has three areas. You'll notice here and this is polar. Oh, nonpolar. This is nonpolar. The linear shape again is nonpolar. You'll notice here that all of the central atoms have more than the 8 valence electrons. So that would mean this would be something like sulfur or phosphorus. So it's in that third period on the periodic table or beyond because we have more than the 8 electrons. So it kind of has those. These have the ability to have those extras. These aren't as common because of that exception, but it's still a good to know these shapes. And then last but not least, we have the octahedral. So now we have 6 areas, 6 bond areas. The last one had 5. So again, the first one is octahedral, which is nonpolar. We're following the same pattern. This one it's referred to as a square pyramid. If you were to connect the lines here, it would end up having a 4-sided pyramid as opposed to all the other ones which were 3-sided pyramids. And we have electrons down here. So this is polar. And then the last one, this one's kind of a bit odd. We have 2 electron pairs here. It's referred to as square planar. Which is actually nonpolar. This is the only example of a nonpolar substance that you would kind of not expect. Just to kind of keep in mind. I probably would not ask you about this, but just kind of note this is a kind of odd exception here.